sklearngaussianprocesskernelsMatern. Description: the Matern kernel is a stationary kernel that is commonly used in Gaussian process GP regression for modeling smooth functions. It provides a balance between smoothness and flexibility, making it suitable for a wide range of applications. The Matern kernel's smoothness is controlled by a parameter called nu, which dictates the number of derivatives that are continuous. Inputs: X, an array of shape n samples. N features representing the input data points. Each row corresponds to a sample, and each column represents a feature. Y, an array of shape n samples, or n samples. N targets representing the target values corresponding to the input data points. Outputs: a covariance matrix of shape n samples. N samples, representing the pairwise covariances between the input data points. A predicted output value for a new input data point, along with the associated uncertainty variance. Steps: calculate the distance between input data points. The kernel function is based on the distance between input data points. The distance can be calculated using various metrics, such as Euclidean distance, Manhattan distance, or other distance metrics appropriate for the specific application. Apply the Matern kernel function. The Matern kernel function is then applied to the calculated distances to determine the covariance between the input data points. The function involves a combination of exponential and Bessel functions. Compute the covariance matrix. The pairwise covariances between all input data points are calculated and stored in a covariance matrix. This matrix is used in GP regression to infer the relationships between the data points. Metrics: log likelihood measures the goodness of fit of the GP model to the data. Higher values indicate a better fit. Mean squared error MSE measures the average squared difference between the predicted and actual target values. Lower values indicate better prediction accuracy. Visualization plots: kernel function visualization, plotting the Matern kernel function with varying distance values and new parameters can help understand the effect of these parameters on the smoothness of a kernel. Predicted function visualization, plotting the predicted function along with the confidence intervals based on the uncertainty can visualize the GP model's predictions and the associated uncertainty. Fine-tune parameters. Nu, this parameter controls the smoothness of the kernel. Higher values of nu lead to smoother functions. Common values for nu include 1.5, 2.5, and 52. Length scale: this parameter determines the characteristic length scale of the function. Larger values indicate smoother functions that vary slowly. Uncertainty methods. Marginal variance provides a measure of the uncertainty in the predicted value at a given input data point. Confidence intervals constructs a range around the predicted value, representing the interval within which the true value is likely to fall with a certain probability. Challenges and fixes. Challenge 1: overfitting. When the model is too complex, it can fit the training data too closely and fail to generalize well to unseen data. Sample use case that resulted in challenge 1: a GP model with a high nu value and a small length scale is used to fit a noisy dataset. Fixes to challenge 1: regularization. Introduce a penalty term in the model's objective function to discourage overly complex models. Cross-validation. Split the data into training and validation sets. Train the model on the training set and evaluate its performance on the validation set. Challenge 2: poor performance on data with complex dependencies. The Matern kernel may struggle to capture highly nonlinear relationships in the data. Sample use case that resulted in challenge 2: using a Matern kernel to model a dataset with strong periodic patterns. Fixes to challenge 2: Use a different kernel. Consider using a more flexible kernel, such as the rational quadratic kernel or a custom kernel designed for the specific data. Characteristics. Feature engineering. Transform the input features to capture the underlying dependencies in the data. Multi-output GP. Utilize a multi-output GP model to capture the complex relationships between multiple output variables.